In the vast expanse of deep space, billions of light years from Earth, there exists a gravitational anomaly so extreme that it challenges the very fabric of our understanding. Ton 618. The name itself carries weight in astronomical circles, not just because of what it represents, but because of the sheer impossibility of its existence. This is no ordinary celestial object. It is the largest known black hole in the observable universe, a cosmic monster that defies every theoretical limit we have established about how massive a single object can become. To call Ton 618 massive is to understate reality by an almost incomprehensible margin. The supermassive black hole at its core contains a mass equivalent to approximately 66 billion times that of our Sun. 66 billion. To place that in perspective, if you could somehow gather every star, planet, moon, asteroid, and particle of dust in our entire solar system and compress it down to a singularity, you would still fall spectacularly short of even 1/1000th of Ton 618's mass. The Sun itself, that brilliant furnace that sustains all life on Earth, becomes less than a grain of sand when measured against this Leviathan. This object represents what astrophysicists cautiously refer to as the upper theoretical limit of black hole physics. Beyond this scale, the known laws that govern accretion, growth rates, and gravitational equilibrium begin to break down. The density concentrated at its core warps space-time so dramatically that the surrounding region operates under fundamentally different physical rules than the rest of the universe. Light bends, time dilates, and matter spirals inward at velocities approaching the speed of light itself. The gravitational pull is so overwhelming that it could theoretically engulf entire solar systems, not once, but multiple times over, swallowing them whole without pause or resistance. Ton 618 is not simply a black hole, it is the biggest single gravitational force object humanity has ever detected. It sits alone in a category reserved for the most extreme phenomena the cosmos can produce. In the hierarchy of cosmic violence, it occupies the throne. Nothing else we have observed comes close to matching its scale or its power. Astronomers describe it not just as an outlier, but as a fundamental benchmark, a living proof that the universe is capable of producing structures far more extreme than our models originally allowed. Located at an incomprehensible distance of over 10 billion light years away, Ton 618 exists in a region of space so remote that the light we observe today began its journey long before Earth even had multicellular life. We are not seeing it as it is now. We are seeing it as it was billions of years ago, frozen in time by the finite speed of light. What it has become in the present remains unknown. It could be larger still. It could have consumed even more matter. Or perhaps it has quieted, its fuel exhausted. We cannot know. All we have is the ancient light carrying with it the story of a monster that once burned brighter than entire galaxies. This is Ton 618, a true leviathan of the cosmos, a black hole so large it seems to mock the very idea of physical limits. It does not simply challenge what we know about the universe, it rewrites the rules entirely. And yet, for all its terrifying scale, it began not with a roar, but with a mistake, a cataloguing error made decades ago in a small observatory far from the centres of astronomical power. The story of how we discovered this cosmic giant is as remarkable as the object itself. The story of how humanity first encountered Ton 618 begins not with cutting-edge technology or deliberate search, but with the stroke of pure chance. The year was 1957. The location was Mexico at the Tonantzintla Observatory, a modest facility perched in the high-altitude plains where the air was thin and the skies remarkably clear. It was here, amid routine photographic surveys of the night sky, that an astronomer catalogued a faint blue speck among thousands of similar dots scattered across the photographic plates. The object was assigned a simple designation drawn directly from the observatory's name, TON 618. Nothing about it suggested importance, nothing hinted at the cosmic scale hidden within that tiny point of light. At the time, the object was mislabeled as a faint blue star. This was not an error born of carelessness, but rather a limitation of the era's observational capacity. In 1957, astronomy relied heavily on photographic emulsions and optical telescopes. Spectroscopy was still in its infancy as a widespread tool. The instruments available could capture light, measure brightness, and record position, but they could not easily penetrate deeper into the nature of distant objects. A blue dot on a plate could be a nearby star, a distant galaxy, or something else entirely. Without further analysis, astronomers catalogued what they saw and moved on. TON 618 was filed away as just another entry in the growing list of celestial coordinates. Unremarkable, forgotten. For nearly a decade, TON 618 stayed unnoticed. It sat quietly in the archives, a single line in a reference catalogue that few ever consulted. The technology of 1957 was simply not ready to reveal its truth. Photographic surveys of that period were designed for breadth, not depth. They swept across wide swathes of sky, capturing thousands of objects in each frame, but the resolution and sensitivity were insufficient to distinguish between fundamentally different types of sources. A faint blue star and an incredibly distant, incredibly luminous quasar could appear nearly identical on such plates. The light reached the film, but the information it carried remained locked, inaccessible. What TON 618 actually represented was a hidden giant disguised by distance and limited instrumentation as a small, insignificant dot. The object was quietly waiting, not in the sense of intention, but in the sense that its true nature would only become apparent when human technology advanced far enough to decode the light it had been sending across the universe for billions of years. The astronomers who first recorded it had no way of knowing they had captured something extraordinary. They saw a speck. They catalogued it. They moved on to the next frame. The breakthrough came later, in the late 1960s, when advances in spectroscopy and radio astronomy began to revolutionize the field. Astronomers were no longer limited to simply recording the brightness and color of distant objects. They could now split that light into its component wavelengths, analyzing the spectral fingerprints embedded within. They could detect radio emissions, revealing objects that were virtually invisible in optical light, but screamed across the electromagnetic spectrum at other frequencies. It was during this period of rapid technological expansion that TON 618 was reobserved, and everything changed. When the new data arrived, the object that had once seemed so ordinary revealed itself to be something entirely different. TON 618 was not a star. It was not even a galaxy in the conventional sense. It was a quasar, one of the brightest and most energetic objects in the entire universe. The term quasar itself is derived from quasi-stellar radio source, a name given in the early days of radio astronomy when these objects first appeared as star-like points that emitted powerful radio waves. But quasars are not stars. They are the intensely luminous cores of distant galaxies, powered by supermassive black holes actively consuming matter at prodigious rates. The light we see comes not from the black hole itself, which emits nothing, but from the superheated accretion disk of gas and dust spiraling inward at nearly the speed of light, radiating energy across the entire electromagnetic spectrum. TON 618 sits in the sky between the constellations Canes Venatici, also known as the hunting dogs, and Coma Berenices, named after the hair of Queen Berenice. Its position is unremarkable in terms of its celestial coordinates, but what it represents in terms of physical scale is anything but ordinary. This ultraluminous beacon became an object of intense scientific interest almost immediately upon its reclassification. Astronomers began directing more powerful instruments toward it, gathering data across multiple wavelengths, measuring its brightness, its spectrum, its variability. With each new observation, the picture grew clearer and more astonishing. TON 618 was classified as a radio-loud quasar, meaning it emits significant energy, not just in visible light, but across radio frequencies as well. This indicates that the processes occurring near its event horizon are extraordinarily violent, generating magnetic fields and particle jets strong enough to beam radiation across intergalactic distances. The levels of energy being released were insane by any measure, far exceeding anything produced by normal stellar processes. This was not fusion. This was gravitational energy conversion, matter being torn apart and accelerated to relativistic speeds, releasing energy with an efficiency that no chemical or nuclear process could match. Even in those early observations, TON 618 appeared suspiciously powerful. The brightness measurements were off the charts. The spectral lines indicated enormous redshift, meaning the object was receding from us at tremendous velocity due to the expansion of the universe itself, placing it at a cosmological distance almost unimaginable. And yet, despite that distance, despite the billions of light years separating us, the object was still bright enough to be detected and studied. That alone hinted at something exceptional. A quasar, visible across such a span of space and time, must be radiating energy on a scale that defied easy comprehension. By the time the full implications became clear, TON 618 had transformed from a forgotten catalogue entry into one of the most scientifically significant objects ever discovered. It had gone from a mislabeled star to a cosmic powerhouse, from obscurity to prominence, all because technology had finally caught up to the information embedded in its ancient light. What had once been dismissed as unremarkable was now recognized as a monster, a gravitational engine of almost unthinkable scale. The small dot catalogued in Mexico in 1957 had become a landmark in the history of astronomy, and the real surprises were only just beginning. By the time TON 618 emerged from obscurity, astronomy itself had changed. The sky was no longer just a pattern of stars and nebulae. It had become a laboratory, and light was the data. Spectrographs, radio receivers, and early digital detectors turned that once anonymous blue speck from Tonantzintla into something far stranger. What had been labelled as a faint star refused to behave like one. Its spectrum was stretched, its lines displaced, its brightness out of proportion to any normal stellar object. The more closely astronomers examined it, the clearer one conclusion became. This was not a star at all. It was a quasar, one of the brightest categories of objects the universe has ever produced. To understand why that realization was so important, imagine what a quasar actually is. At the center of a distant galaxy, a supermassive black hole feeds on surrounding gas and dust. As matter falls inward, it does not plunge directly into the event horizon. It forms a rotating accretion disk, a flat, swirling structure where particles collide, compress, and heat to extraordinary temperatures. Friction, magnetic fields, and relativistic motion drive the gas to millions of degrees, hot enough to radiate energy across the entire electromagnetic spectrum. The result is a point-like source that, from our vantage point, can outshine the combined starlight of the entire galaxy that hosts it. TON 618 was one of these engines, but on a scale that pushed the very edges of theory. Its position in the sky is modest. TON 618 lies in a region between the constellations Canes Venatici and Coma Berenices, far from the bright guide stars that amateurs typically use for navigation. Through a small telescope, it is not a dramatic sight. It appears as a tiny, faint speck, lost among countless other points of light. Yet hidden in that dot is a beacon visible across more than 10 billion light-years of expanding space. The contrast between appearance and reality is almost absurd. To the naked eye, nothing. To a trained instrument, one of the loudest signals in the cosmos. When higher resolution observations arrived, TON 618 revealed another crucial property. It was radio loud. In quasar terminology, that phrase does not mean simply that it emits radio waves. Many objects do that. It means that its radio emission is exceptionally strong relative to its optical output. This typically indicates the presence of powerful relativistic jets, streams of charged particles, accelerated to velocities close to the speed of light and launched along the black hole's rotational axis by twisted magnetic fields. These jets can extend for hundreds of thousands of light years, punching through the surrounding galaxy and dumping energy into intergalactic space. For TON 618, the radio emission marked it as an especially active and energetic system. From the very first serious studies, the numbers associated with TON 618 were suspiciously large. Its redshift, a measure of how much the expansion of the universe has stretched its light, placed it at an enormous distance. That in turn implied a staggering intrinsic luminosity. Even after accounting for the dimming due to distance, the amount of power required to make it appear as bright as it does from Earth was far beyond ordinary galaxies. This was a cosmic searchlight operating in an early epoch of the universe, when galaxies were younger, mergers more common, and black hole growth more aggressive. For astronomers, this made TON 618 an ultra-luminous beacon, a reference point in the deep universe. Because its light has travelled for billions of years to reach us, observing it is equivalent to looking back in time. The quasar phase we see corresponds to a period when the universe itself was far younger and denser. That makes TON 618 not only an object of interest on its own, but also a probe of its environment. The light passing through intergalactic gas on its journey carries subtle signatures of the material it traversed. By analysing these imprints, researchers can learn about the large-scale structure of the cosmos during that earlier era. As more data accumulated, TON 618 moved rapidly from a curiosity to a priority target. Its spectrum became a classroom in itself. Wide, broadened emission lines revealed gas moving at immense velocities near the black hole, while absorption features traced intervening matter between us and the source. Every part of the signal told a different part of the story. The broad line region near the black hole, the slower moving gas farther out, the intergalactic medium that the light crossed during its flight. The object was no longer just a point, it was a layered structure written into the wavelengths of its radiation. The classification as a quasar also recontextualized the earlier mislabeling. In the 1950s and even early 1960s, it was entirely reasonable to mistake such objects for stars. On photographic plates they appeared stellar, unresolved, with no visible surrounding galaxy. Only once redshift measurements became routine did the true distances emerge, and with them the realization that their apparent brightness at such distances required extreme energy sources. Ton 618 fit this pattern, but amplified it to an almost uncomfortable degree. It was not simply another quasar, it was an outlier among outliers. Quasars, in general, are feeding black holes, caught during episodes when large amounts of gas are funneled into their gravitational wells. In that sense, they are black holes on fire, not in the literal sense, since nothing can burn in the vacuum around a singularity, but in the energetic sense, with accretion converting gravitational potential energy into light with remarkable efficiency. Around Ton 618, that process appears to operate near the upper extremes of what our models allow. It radiates so intensely that the outward pressure of its own light should, in principle, push back on infalling gas and regulate the growth of the black hole at its centre. The fact that the central mass still reached tens of billions of solar masses tells us that whatever feeding history it experienced was both prolonged and unusually effective. From the day its quasar nature was confirmed, Ton 618 became a test bed for high-energy astrophysics. It forced theorists to refine models of accretion, jet formation, and black hole evolution. It entered discussions about how such massive objects could form so early in cosmic history. It appeared in catalogue after catalogue as one of the most extreme known examples of active galactic nuclei, and above all, it served as a reminder that the universe is not obliged to respect human intuitions about what is reasonable. In the earlier parts of this story, Ton 618 was a nameless speck, a mistaken star. With its quasar identity established, it had become something else entirely. A lighthouse shining from the distant past, powered by a gravitational well so deep that not even light could climb out once it crossed the horizon. The brightness, however, did escape, generated just outside that fatal boundary by matter in its final catastrophic orbit. That light was only the beginning. Once astronomers understood how bright Ton 618 truly was, they began to ask the next question: how bright can such an object become before even our language for extreme phenomena starts to fail? By the time astronomers understood that Ton 618 was not a star but a quasar powered by an ultramassive black hole, the next shock came from a simple but unforgiving calculation. How bright was it really? Not how bright it looked from Earth, dimmed by unimaginable distance, but how much energy it must be producing at its source to remain visible across more than 10 billion light-years of expanding space. When the numbers were finally pinned down, they did not just stretch expectations, they shattered them. The luminosity of Ton 618 is estimated to be comparable to the combined output of roughly 140 trillion suns. That is 140 trillion stars, each radiating energy like our sun, all condensed into a single point-like source at the heart of a distant galaxy. No ordinary galaxy even comes close to matching that intensity from a single region. Entire galactic systems containing hundreds of billions of stars can be outshone by this one quasar. It is, quite literally, among the brightest persistent objects that humanity has ever detected in the universe. To appreciate what that means, consider what a single sun does. Our star floods the solar system with light and heat, drives climate, powers photosynthesis, and carves shadows across every surface on Earth. Multiply that by 1 trillion and then by another 140, and you begin to approach the energy scale radiated near the event horizon of TON 618. This radiation is not coming from the black hole itself, which remains dark and inescapable. It is coming from the accretion disk, the maelstrom of gas and dust spiraling inward, compressed and heated until atoms are stripped of their electrons and matter glows in ultraviolet and X-ray wavelengths as well as visible light. Yet despite this almost incomprehensible power, TON 618 appears to us as only a faint speck in our telescopes. The reason is distance. The quasar lies about 10.4 billion light-years away. The light we record from it today left the source when the universe was less than a third of its current age. When that light began its journey, our Milky Way was still assembling, and the Sun and Earth did not yet exist. Every photon we detect from TON 618 is a messenger from deep cosmic time, an echo of a phase of extreme activity that occurred billions of years before our planet formed. Because of that distance, what we see is not TON 618 as it is now, but as it was 10.4 billion years ago. In cosmology, time and distance are inseparable. Looking outward is the same as looking backward. The quasar we measure might have changed dramatically since then. Its fuel supply could have diminished. Its jets could have shut down. The accretion disk might have faded as the central black hole exhausted the gas reservoir in its host galaxy. Or the black hole could have grown even larger, drawing in still more matter from its surroundings. Our instruments cannot show us its current state. They only reveal its past. Even in that ancient snapshot, however, TON 618 already outshines entire galaxies. To say that it is luminous is not enough. Its energy output places it among the greatest light sources known in the universe. It acts like a cosmic lighthouse, projecting radiation across intergalactic space, cutting through the intervening darkness with a beam that remains detectable after travelling for billions of years. For astronomers, such an object is both a challenge and a gift. A challenge, because explaining how a black hole can grow and feed to sustain that level of brightness pushes models of accretion and feedback to their limits. A gift, because that same brightness makes the object visible across extraordinary distances, allowing it to serve as a probe of the young universe. The fact that we can still detect TON 618 at all, given its distance, is itself evidence of its phenomenal intrinsic power. The intensity of light decreases with the square of distance. Double the distance and the observed brightness drops by a factor of 4. Increase the distance to billions of light years and almost every ordinary source fades below detectability. For TON 618 to remain visible under that penalty, its true luminosity must be huge. It is only because it is so outrageously bright that modern telescopes can pull its signal out of the noise. At the heart of this brightness sits the same engine that defines all quasars, a feeding black hole. As gas falls inward, gravitational potential energy is converted into radiation with extraordinary efficiency. In a typical accreting system, up to roughly 10% of the rest mass energy of the infalling matter can be released as light before the material crosses the event horizon. By contrast, nuclear fusion in stars converts less than 1% of rest mass into energy over their lifetimes. This is why a single black hole with an active accretion disk can rival or exceed the output of hundreds of billions of stars. TON 618 simply operates that mechanism on an extreme scale. The brightness is not uniform in all directions. The structure around the black hole is complex. There is the inner accretion disk, a surrounding region of fast-moving gas that produces broad emission lines, and sometimes large-scale jets beaming radiation along particular axes. Orientation matters. If we happen to view the quasar from a favourable angle, we can see deeper into the most energetic regions. In the case of TON 618, whatever geometry nature has chosen, the net effect is amplification. The line of sight we possess intersects with a region of intense activity, turning the quasar into a reference point visible across much of the observable universe. All of this energy, all of this light, comes from a single gravitational well. It is easy to focus on the radiance and forget what it implies. Every photon escaping that environment is the byproduct of matter losing energy and angular momentum, inexorably spiraling closer to the horizon. The same hunger that makes TON 618 shine also ensures that its growth continues. The more it eats, the more luminous it becomes, up to the point where radiation pressure pushes back on infalling material. The brightness of TON 618 is therefore a direct measure of its appetite at the epoch we observe. It is not a quiet, dormant black hole. It is one caught in the act of violent feeding. Seen in this light, the quasar is both a spectacle and a warning. It shows us that there exist places in the universe where gravity, motion, and radiation reach extremes that our minds struggle to visualize. It demonstrates that a single compact object can dominate the energy budget of an entire galaxy. And it raises a deeper question that will guide the next step in this story. If a black hole can radiate with the power of 140 trillion suns and still continue to grow, just how massive can such an object become? In the case of TON 618, the answer takes us beyond luminosity and directly into the staggering scale of the black hole itself. Once astronomers had confirmed that TON 618 was a quasar, radiating with the intensity of 140 trillion suns, the next logical question became unavoidable. What kind of black hole could power such an engine? The answer, when it finally emerged from detailed spectroscopic analysis of the gas orbiting near the event horizon, was staggering even by the extreme standards of supermassive black holes. The central mass of TON 618 is estimated to be approximately 66 billion times the mass of our Sun. 66 billion solar masses concentrated into a single gravitational singularity. To grasp what that number represents, start with the Sun. Our star contains more than 99% of all the mass in the solar system. It is massive enough to hold 8 planets, countless asteroids, comets and moons in its gravitational grip across billions of kilometers of space. Yet compared to TON 618, the Sun would appear as nothing more than a grain of sand beside a mountain. Even that comparison fails to capture the disproportion. A grain of sand is visible. A single sun beside TON 618 would be lost entirely, drowned in the sheer enormity of the scale difference. TON 618 is not just one of the most massive black holes ever discovered. It is one of the heaviest objects known in the observable universe. Its mass exceeds the combined total of all the stars in the Milky Way galaxy, which amounts to roughly 64 billion solar masses. Think about that for a moment. Our entire galaxy, with its estimated 200 to 400 billion stars, all the gas, dust, planets and dark matter distributed across a spiral disk, 100,000 light-years wide, collectively weighs slightly less than the single black hole at the core of TON 618. It is a cosmic heavyweight beyond comparison. The existence of such an enormous black hole raises immediate theoretical challenges. In models of black hole growth, there are constraints on how quickly matter can be accreted. When material falls toward a black hole, it heats up and radiates energy. That outward radiation pressure pushes back against the infalling gas. There is a balance point known as the Eddington limit, where the radiation pressure equals the gravitational pull. Beyond that limit, further accretion becomes difficult because the black hole essentially pushes away its own fuel. For a black hole to grow to 66 billion solar masses, it must either have fed for an extraordinarily long time, exceeded the Eddington limit through some mechanism, or both. The theoretical upper limit for supermassive black holes in typical accretion scenarios is estimated to be around 50 billion solar masses for standard parameters. Beyond that threshold, growth slows dramatically. The radiation from the accretion disk becomes so intense that it disrupts the inflow of new material, starving the black hole of fuel. Yet TON 618 sits comfortably above that limit at 66 billion solar masses. This suggests that its formation and growth history involved conditions that were not typical. Perhaps it formed in an especially dense region of the early universe where gas was abundant. Perhaps it underwent multiple mergers with other massive black holes. Or perhaps it found ways to accrete matter more efficiently than standard models predict. In terms of pure gravitational dominance, TON 618 reshapes the space around it violently, mass warps space-time, and the more concentrated the mass, the more extreme the curvature. Near the event horizon of TON 618, space-time is bent so sharply that the geometry of space itself becomes distorted beyond intuition. Clocks would run slower there relative to a distant observer due to gravitational time dilation. Light paths curve dramatically. The tidal forces, the difference in gravitational pull between near and far points, grow intense enough to stretch and compress matter in ways that would shred any ordinary object long before it crossed the horizon. Among known black holes, TON 618 stands as the king. It occupies the throne of the supermassive category and arguably pushes into what some researchers call the ultramassive regime, reserved for black holes exceeding tens of billions of solar masses. This is not a common category. Most supermassive black holes at galaxy centers range from millions to a few billion solar masses. Even Sagittarius A star, the black hole at the center of our Milky Way, has a mass of only about 4 million solar masses. Compared to TON 618, it is a lightweight by more than 4 orders of magnitude. TON 618 is 15,300 times more massive than the black hole anchoring our own galaxy. For scientists attempting to explain how TON 618 came to exist, the mass itself is both a clue and a puzzle. Black holes grow primarily through 2 mechanisms. They can accrete gas and dust from their surroundings, converting gravitational potential energy into radiation in the process, or they can merge with other black holes, combining their masses in catastrophic collisions that release gravitational waves. For TON 618 to have reached 66 billion solar masses, by the time we observe it, roughly 3 billion years after the Big Bang, it would have needed either an exceptionally rich feeding environment or a series of massive mergers, or both operating in tandem over cosmological timescales. The mass of TON 618, also places it near what some models consider the effective growth limit for black holes. Beyond a certain point, the efficiency of accretion drops because the radiation field becomes so strong that it ionizes and heats surrounding gas, preventing it from cooling and falling inward. In this sense, TON 618 may represent a kind of end state, a black hole that grew as large as the physics of accretion would allow under the conditions present in its host galaxy. If true, then TON 618 is not just massive by chance. It is massive because it reached the ceiling imposed by the interplay between gravity and radiation. There is also something almost absurd about a mass this large existing in what is, on cosmic scales, a relatively compact region. The mass is not spread out like a galaxy. It is concentrated within the event horizon, a boundary from which not even light can escape. For 66 billion solar masses, the size of that horizon is enormous by terrestrial standards, but tiny compared to galactic scales. Everything that makes TON 618 what it is, all that mass, all that gravitational influence, exists in a region smaller than our solar system. The density implied by that confinement defies everyday experience. In many ways, TON 618 functions as the ultimate cosmic benchmark. It shows us the upper edge of what nature can construct through gravity alone. It challenges our models of black hole growth and forces refinements to our understanding of how matter behaves under extreme conditions. And it serves as a stark reminder that the universe contains structures whose scale and power exceed anything we encounter in our local cosmic neighborhood. TON 618 is the real-life endgame boss of black hole physics, a gravitational titan that seems to mock the very idea of limits. Yet as overwhelming as the mass is, it is not the only astonishing feature of this object. The physical size of its event horizon, the boundary that marks the point of no return, takes the extremes even further. The mass of TON 618 is extraordinary, but mass alone does not fully convey the physical enormity of this object. To understand the true scale, we must turn to the event horizon, the boundary that defines the edge of the black hole, the point beyond which escape becomes impossible. For a black hole with 66 billion solar masses, the radius of that horizon stretches outward to staggering distances. Current estimates place the event horizon radius of TON 618 at over 1,000 astronomical units. 1,000 astronomical units. That single number contains more spatial horror than most minds can comfortably process. An astronomical unit, abbreviated AU, is the average distance between the Earth and the Sun, approximately 150 million kilometers. It is a convenient yardstick for measuring distances within our solar system. Mercury orbits at roughly 0.4 astronomical units. Earth sits at 1 astronomical unit, Mars at 1.5. Jupiter at 5.2, Saturn at 9.5. Even distant Neptune, the outermost major planet in our solar system, orbits at only about 30 astronomical units from the Sun. Pluto, the dwarf planet that once marked the edge of our known planetary family, travels in an elliptical orbit that reaches roughly 40 astronomical units at its farthest point. Now compare that to the event horizon of TON 618. At over 1,000 astronomical units in radius, the boundary of this black hole is more than 25 times farther from its centre than Pluto is from the Sun. If you were to place TON 618 where our Sun currently sits, its event horizon would extend far beyond the orbit of every planet, every dwarf planet, and every known object in the Kuiper belt. The entire architecture of our solar system, Everything from the Sun to the distant icy bodies at the edge of interplanetary space would fit comfortably within less than 5% of the radius of TON 618's event horizon. It is extraordinarily difficult to visualize a boundary that large. Human intuition evolved to deal with distances measured in meters or kilometers, not astronomical units stretching into the thousands. Yet the geometry is simple and unforgiving. The event horizon is a sphere. For a non-rotating black hole, the radius of that sphere is determined by the Schwarzschild formula, which relates mass directly to horizon size. Double the mass and you double the radius. For TON 618, with its 66 billion solar masses, the radius scales proportionally. The result is a gravitational boundary so vast that light itself would take weeks to cross from one side to the other. Consider what that means in practical terms. Light travels approximately 300,000 kilometers per second. At that speed, light crosses the distance from the Earth to the Moon in just over 1 second. It reaches Mars in a few minutes. It crosses the orbit of Pluto in about 5.5 hours. But to traverse the full diameter of TON 618's event horizon from one edge to the other, light would require multiple weeks. That is not a region. That is a domain, a territory carved out of space-time so large that even the fastest thing in the universe takes significant time to navigate it. The curvature of space-time in the vicinity of TON 618 is extreme and horrifying. Near the event horizon, gravity dominates everything. Geodesics, the paths that freely falling objects follow through curved space-time, spiral inward with no possibility of reversal. Once an object crosses that boundary, whether it is a particle, a photon, or a spaceship, no force in the universe can bring it back. The escape velocity at the horizon is exactly the speed of light, which means that even light, travelling at the maximum speed allowed by physics, cannot escape. Anything slower is doomed. The gravitational pull surrounding TON 618 reshapes not just trajectories but the very fabric of reality. Space stretches, time dilates. An observer falling toward the horizon would experience time differently than someone watching from a safe distance. From the perspective of that distant observer, the infalling object would appear to slow down, its light redshifting and dimming as it approached the boundary, asymptotically approaching the horizon but never quite seeming to cross. From the perspective of the infalling observer, however, the crossing would happen in finite time, though what awaits beyond is unknowable. The singularity at the centre, where space-time curvature becomes infinite, remains hidden behind the horizon. Nothing that enters the event horizon can ever send a signal back to the outside universe. No light, no radiation, no information of any kind. The horizon is a one-way membrane, a boundary that permits passage inward but forbids any outward communication. In this sense, the interior of TON 618 is causally disconnected from the rest of the cosmos. Whatever falls in is lost forever to external observers. That isolation is absolute, enforced not by physical barriers but by the geometric structure of space-time itself. The scale of the event horizon also has implications for how TON 618 interacts with its surroundings. A black hole with a horizon spanning more than 1,000 astronomical units can engulf entire star systems without difficulty. If a binary star system were to wander too close, both stars could be swallowed in a single pass. A dense molecular cloud drifting into the vicinity would be shredded and consumed, its gas heated to millions of degrees as it spiraled inward. Even the collision of another galaxy with the host of TON 618 would funnel gas and stars toward the central black hole, feeding it and potentially triggering even greater luminosity. It is worth pausing to reflect on the fact that this boundary, vast as it is, surrounds a region where our current understanding of physics breaks down. General relativity describes space-time curvature and predicts the existence of singularities, points where curvature becomes infinite and classical descriptions fail. Quantum mechanics governs the behavior of matter and energy at the smallest scales but does not yet reconcile with gravity in extreme regimes. At the core of TON 618, hidden behind the event horizon, these two pillars of modern physics collide. We do not know what truly happens there. We can only describe the horizon and the region outside it. The event horizon also serves as the ultimate gravitational trap. Any object passing within a certain radius, even if moving at high speed, will find its trajectory bent inward. There is a region around every black hole called the photon sphere, where light can orbit in circular paths, though such orbits are unstable. Closer still is the innermost stable circular orbit, the last place where matter can orbit, without inevitably spiraling inward. For TON 618, even these zones lie at distances comparable to the orbits of outer planets in our solar system. The reach of its gravity is simply enormous. To call TON 618 Solar System Swallower is not hyperbole. It is a straightforward description of its capacity. The event horizon alone is large enough to engulf our entire solar system many times over. The tidal forces near the boundary would tear apart planets, moons, and any structure not held together by forces stronger than gravity. The radiation environment surrounding the black hole, generated by the accretion disk, would sterilize any approaching object long before it reached the horizon. In every sense, TON 618 is an engine of destruction operating on a scale that makes even stellar explosions seem modest by comparison. And yet, for all its menace, the black hole itself remains invisible. We cannot see the event horizon directly. We can only infer its presence from the behavior of matter and light around it. The true face of TON 618 is hidden, masked by its own gravity. What we observe instead is the light from the accretion disk, the brilliant corona of doomed matter in its final moments before crossing the point of no return. That light tells the story of the black hole's hunger, and it is to that light and the physics that generates it that the story now turns. The event horizon of TON 618 is vast and inescapable, but it remains invisible. Black holes emit no light of their own. The singularity at the core is hidden behind the horizon, and nothing that crosses that boundary can send information back to the outside universe. So, how do we see TON 618? At all. How does an object defined by its absolute darkness become one of the brightest things in the cosmos? The answer lies not in the black hole itself, but in the inferno that surrounds it. The accretion disk, the quasar engine, the visible face of gravitational hunger. We do not observe the black hole directly. What we see instead is the superheated material spiraling inward toward the event horizon. As gas and dust from the surrounding galaxy fall toward TON 618, they do not plunge straight in. Conservation of angular momentum forces the material into a rotating disk, a flattened structure where particles orbit the black hole at velocities approaching the speed of light. Within this disk, friction, magnetic fields and turbulence drive the gas inward, while simultaneously heating it to extraordinary temperatures. The temperatures reached in the accretion disk around ton 618 are almost incomprehensible. In the innermost regions, closest to the event horizon, gas heats to millions of degrees Kelvin. At those temperatures, atoms are fully ionized. Electrons are stripped away, leaving bare nuclei. The gas becomes a plasma, a state of matter so energetic that it radiates across the entire electromagnetic spectrum: ultraviolet, X-rays, gamma rays, visible light, infrared, radio waves. Every wavelength carries away energy generated by the violent descent of matter into the gravitational well. This process converts gravitational potential energy into radiation with remarkable efficiency. As matter falls deeper into the potential well of the black hole, it loses energy. That energy does not simply disappear. It is transformed into heat and light, radiated outward into space. In an efficiently accreting black hole, up to 10% of the rest mass energy of the infalling material can be released as radiation before it crosses the event horizon. By contrast, nuclear fusion in stars converts less than 1% of rest mass into energy over billions of years. The accretion process is, gram for gram, far more efficient than stellar burning. For ton 618, with its mass of 66 billion suns, the accretion disk is correspondingly enormous. The disk extends outward from the event horizon for vast distances, possibly spanning light years. The outer regions are cooler, glowing in infrared and radio wavelengths. The middle zones radiate invisible and ultraviolet light. The innermost regions, where the gas reaches its peak temperature just before crossing the horizon, blaze in X-rays and gamma rays. The entire structure acts as a cosmic furnace, melting space with the sheer intensity of its output. The energy emitted by this accretion engine is what makes ton 618 visible across more than 10 billion light years. The luminosity of 140 trillion suns does not come from the black hole, it comes from the disk. Every photon we detect from ton 618 originated in that swirling maelstrom of doomed matter. The radiation pressure is so intense that it pushes outward on surrounding gas, regulating the rate at which new material can fall in. This is the Eddington limit in action. The black hole generates so much light from feeding that the light itself begins to choke off the supply of fuel. Yet despite this self-regulating mechanism, ton 618 has clearly been feeding at a prodigious rate for millions of years. Quasars are not steady, eternal beacons. They are phases in the life of a galaxy, periods when large amounts of gas are funneled toward the central black hole, triggering intense accretion and luminosity. Eventually the fuel runs out, the disk fades, the quasar shuts down. But at the epoch we observe, ton 618, it is still in full blaze. The non-stop feeding frenzy continues, pouring energy into the surrounding space at a rate that outshines entire galaxies. The light from the accretion disk does more than illuminate, it carries information. By analysing the spectrum of that light, astronomers can measure the velocity of gas orbiting near the black hole. Doppler shifts reveal material moving toward us and away from us at thousands of kilometers per second. The width of spectral emission lines tells us about the range of velocities present in the disk. From those measurements, we can apply Kepler's laws and estimate the mass enclosed within the orbit. That is how the 66 billion solar mass figure was derived. The gas motion reveals the gravitational pull, and the gravitational pull reveals the mass. The accretion disk around ton 618 has been shining for millions of years, possibly tens of millions. Quasar lifetimes vary, but they typically last between 10 million and 100 million years before the fuel supply dwindles. During that time, the black hole grows steadily, converting infalling matter into mass and radiation. The light we see now is a snapshot from that active phase, frozen in time by the finite speed of light. By the time we observe it, the quasar may have already shut down in its local present, but we will not know for billions of years until the light from that quieter era finally reaches us. The radiation produced by the accretion disk is far more than just visible light. The disk emits across all wavelengths, creating what astronomers call a continuum spectrum. Overlaid on that continuum are emission lines, specific wavelengths where atoms in the surrounding gas absorb and re-emit energy. These lines are broadened by the Doppler effect due to the high velocities in the disk, creating what is known as the broad line region. Farther out, where velocities are lower, narrower emission lines form. Together, these features paint a detailed picture of the environment surrounding the black hole. The sheer power output of the disk also affects the host galaxy. The radiation and winds driven by the accretion process can heat and expel gas from the galaxy, suppressing star formation. This is known as feedback, a mechanism by which the black hole regulates its own growth and the evolution of its host. For a black hole as massive as TON 618, the feedback effects must have been dramatic, possibly reshaping the entire structure of the galaxy over cosmological timescales. In many ways, the accretion disk is the true star of the show. It is the visible manifestation of the black hole's hunger. It converts invisible gravitational energy into brilliant detectable radiation. It allows us to study an object that is, by definition, dark and unreachable. Without the disk, TON 618 would be invisible, a gravitational ghost. With the disk, it becomes a cosmic spectacle, a fireworks display of physics operating at the edge of what nature allows. The light from the accretion disk also serves a deeper purpose. It keeps the universe glowing. Quasars like TON 618 were far more common in the early universe, when galaxies were smaller, gas was more abundant, and mergers were frequent. Their combined light contributed to the ionization of intergalactic hydrogen, helping to clear the fog that filled space in the first billion years after the Big Bang. In this sense, the hunger of black holes played a role in shaping the transparency of the universe itself. But even as the accretion disk shines with unimaginable intensity, the black hole at the center remains fundamentally invisible. The horizon is there, lurking beneath the glare, swallowing everything that crosses it. The disk is the messenger, the black hole is the void, and between them lies one of the most extreme environments in the universe, a region where matter, energy, and space-time are pushed to their absolute limits. That interplay between light and darkness, visibility and invisibility, is what makes TON 618 both a spectacle and a mystery. The disk shows us where the black hole is, but it cannot show us what the black hole truly is. Despite everything we have established about TON 618, despite the 66 billion solar mass black hole, despite the event horizon spanning over 1,000 astronomical units, despite the accretion disk blazing with the luminosity of 140 trillion suns, the object appears in our most powerful telescopes as nothing more than a faint speck, a single point of light, barely distinguishable from countless other dim sources scattered across the sky. The contrast between its true nature and its visual appearance is almost absurd. This is not a failure of our instruments, it is a consequence of distance and a reminder of just how vast the universe truly is. TON 618 lies more than 10 billion light years away from Earth. To put that in perspective, the light we receive from it today has been travelling through space for over 10 billion years. When that light began its journey, the universe was less than a quarter of its current age. The solar system did not exist. The Milky Way was still assembling from smaller protogalactic fragments. The Earth, the Sun, and everything familiar to us had not yet formed. The photons arriving at our detectors now are ancient messengers, carrying information encoded billions of years ago. Distance does more than separate us from TON 618 in space. It separates us in time. Looking outward in the universe is equivalent to looking backward through its history. Every distant object we observe is a window into the past. The farther away something is, the older the light we see. For TON 618, we are observing a snapshot from when the universe was young, dense, and filled with gas. The quasar phase we witness corresponds to an era of violent galaxy growth and black hole feeding. What TON 618 looks like now, in its local present, remains unknowable. The light from its current state will not reach us for billions of years. The faintness of TON 618 in our telescopes is a direct result of the inverse square law. Light spreads out as it travels. The intensity decreases with the square of the distance. Double the distance and the brightness drops by a factor of 4. Increase the distance to billions of light years and the dimming becomes extreme. For TON 618 to remain detectable across such a span, its intrinsic luminosity must be colossal. If it were any less bright, it would fade below the detection threshold entirely. The fact that we can see it at all is proof of its insane luminosity. Yet despite that luminosity, the object occupies only a single pixel in most images. It does not appear as a disk or a nebula. It does not show structure. It is a point source, unresolved, indistinguishable in shape from a nearby star except for its spectrum and redshift. That point contains more energy, more mass, and more gravitational influence than entire galactic clusters in our local universe. The invisibility of scale is one of the humbling aspects of astronomy. The most extreme objects often look the least impressive through the eyepiece. Every photon we capture from TON 618 is ancient history. Each one started its journey in the accretion disk when the universe was fundamentally different. The rate of cosmic expansion was higher. The density of matter was greater. The large-scale structure of galaxy filaments and voids was less pronounced. The photons travelled through intergalactic space, passing through clouds of hydrogen, avoiding dense regions, redshifting as the universe expanded beneath them. By the time they reach Earth, they have been stretched to longer wavelengths, their energy diluted by the expansion of space-time itself. This redshift is how we measure distance to objects like TON 618. The stretching of light due to cosmic expansion shifts spectral lines toward the red end of the spectrum. The amount of shift is proportional to how much the universe has expanded since the light was emitted. By measuring the redshift, astronomers can calculate the distance and the age of the light. For TON 618, the redshift places it firmly in the early universe, a time when quasars were more common and black hole growth was more aggressive. The ancient light also carries signatures of the material it passed through. As the photons travelled across billions of light years, they encountered intergalactic gas. Neutral hydrogen in those clouds absorbed specific wavelengths, leaving imprints in the spectrum. These absorption features allow astronomers to map the distribution of gas along the line of sight, probing the large-scale structure of the universe at different epochs. In this way, TON 618 serves not only as an object of study in itself, but also as a cosmic backlight, illuminating the gas between us and it. The visibility of TON 618, faint as it is, represents a triumph of observational astronomy. Detecting a point source this dim requires long exposure times, sensitive detectors, and careful data processing. Ground-based telescopes must contend with atmospheric distortion, light pollution, and weather. Space-based telescopes avoid those issues but have limited observing time and must be carefully targeted. Every image of TON 618 is the product of hours or days of accumulated photons, each one a rare visitor from a distant era. The fact that we can study TON 618 in detail, despite its distance, speaks to how far technology has advanced since the 1950s, when it was first catalogued. Modern spectrographs can dissect its light into thousands of wavelengths, revealing chemical compositions, velocities, and temperatures. Radio telescopes can detect emissions invisible to optical instruments. Space telescopes can observe in ultraviolet and X-ray bands that are absorbed by Earth's atmosphere. Together, these tools have transformed a faint speck into a richly detailed astrophysical laboratory. Yet the paradox remains. TON 618 is one of the most powerful objects in the universe, and it appears as a dot. This is cosmic humility in action. The universe does not scale its wonders to human perception. The most extreme phenomena are often hidden by distance, obscured by dust, or compressed into regions too small or too faint to see without technological aid. Our eyes evolved to see reflected sunlight on Earth. They were never meant to perceive the edges of the observable universe. That we can do so at all is a testament to curiosity, mathematics, and engineering. The tiny dot that is TON 618 also serves as a reminder that appearance and reality are not the same. A speck in a telescope contains a black hole that could swallow our solar system. A faint glow represents energy output exceeding the combined light of 1 trillion galaxies. What looks insignificant from here is, in its own context, a gravitational titan reshaping space-time and dominating its cosmic neighborhood. Distance hides the truth, but it does not diminish it, and that truth extends beyond what we can currently observe. TON 618 exists now, in its local present, in some state we cannot yet see. It may still be feeding, growing larger, radiating with even greater intensity. Or it may have quieted, its fuel exhausted, its accretion disk faded to darkness. We will not know until the light from that era reaches us, billions of years in the future. Until then, we observe the past and infer the present, piecing together the story of a cosmic monster from photons that are older than our planet. The tiny dot in our telescopes is a portal to another time, another state of the universe, and a scale of violence and energy that challenges everything we think we understand. The tiny dot we observe in our telescopes represents TON 618 as it existed over 10 billion years ago, when the universe was only about 3.3 billion years old. That timing is critical. It means we are seeing this black hole at a stage when the cosmos itself was still in its relative infancy, less than a quarter of its current age. Galaxies were smaller, more chaotic, still forming from the gravitational collapse of primordial gas. The intergalactic medium was denser, Mergers between galaxies were more frequent. It was an era of rapid growth and violent restructuring, and yet, even in that young universe, TON 618 had already grown to a staggering 66 billion solar masses. That presents a serious problem. The issue is not that such a massive black hole exists. The issue is that it exists so early. Black holes grow primarily through two mechanisms. They can accrete matter from their surroundings, converting gravitational potential energy into radiation as gas spirals inward, or they can merge with other black holes, combining their masses in cataclysmic collisions. Both processes take time. Accretion is limited by the Eddington rate, the balance point where radiation pressure from the infalling matter pushes back against gravity, choking off the fuel supply. Mergers require the right conditions, galaxies colliding, black holes sinking to the center through dynamical friction, orbits decaying until the final plunge. Under standard assumptions, there simply has not been enough time for a black hole to grow to 66 billion solar masses by the epoch we observe, TON 618. If you start with a stellar mass black hole formed from the collapse of a massive star, you begin with perhaps 10 to 100 solar masses. To reach 66 billion solar masses from that starting point, the black hole would need to grow by a factor of nearly a billion. Even if it accretes continuously at the maximum Eddington rate, the exponential growth timescale is on the order of tens of millions of years per refolding, meaning it takes roughly 50 million years to increase the mass by a factor of 2.7. Do the math and the problem becomes clear. Starting from 100 solar masses and growing at the Eddington limit for 3 billion years could, in principle, produce a black hole of several billion solar masses. But 66 billion is far beyond that. To reach such a mass, the black hole would need to have either started much larger than a stellar remnant or grown faster than the Eddington limit allows, or both. None of those options fits comfortably within standard models of black hole formation and growth. TON 618 grew too fast. This is what makes TON 618 and other ultra-massive black holes in the early universe so puzzling. They should not exist yet. Their presence implies that something unusual happened during the formation and growth phases. Perhaps the seeds were larger than we typically assume. Perhaps the accretion was more efficient. Perhaps the environment was richer in gas, allowing sustained feeding at super Eddington rates. Or perhaps the black holes formed through exotic mechanisms that bypassed the slow, stellar collapse pathway entirely. One possibility is that TON 618 formed from a direct collapse black hole, a scenario in which a massive cloud of primordial gas collapses directly into a black hole without forming a star first. In the early universe, before the first generation of stars enriched the interstellar medium with heavy elements, gas clouds could remain exceptionally hot and unable to cool efficiently. Under the right conditions, such a cloud could collapse catastrophically, forming a black hole with an initial mass of thousands or even hundreds of thousands of solar masses. That head start would dramatically reduce the time required to reach 66 billion solar masses. Another scenario involves supermassive stars. In dense primordial environments, gas could accumulate into stars far more massive than anything we see today, reaching masses of tens of thousands of solar masses or more. Such stars would be unstable and short-lived, collapsing into massive black holes after only a few million years. If TON 618 began as the remnant of such a supermassive star, it would start with a much larger seed mass, easing the growth problem. Mergers also play a role. If the host galaxy of TON 618 underwent multiple collisions with other galaxies in its early history. Each merger could bring additional black holes into the system. As these black holes spiraled inward and coalesced, their masses would combine. A series of major mergers, each doubling or tripling the black hole mass, could accelerate growth beyond what accretion alone allows. The challenge is that mergers take time. The black holes must sink to the galactic center, a process slowed by dynamical friction. Even in a dense, gas-rich environment, it is unclear whether enough mergers could occur quickly enough to produce a 66 billion solar mass black hole within 3 billion years. There is also the possibility that TON 618 simply violated the Eddington limit for extended periods. The Eddington limit is not a hard barrier. It is a self-regulating mechanism where radiation pressure balances gravitational infall. But if the accretion geometry is not spherically symmetric, if the gas falls in along specific directions or through dense filaments, the radiation might escape preferentially along other axes, allowing matter to continue falling in at higher rates. Super Eddington accretion has been observed in some systems, and it could, in principle, boost growth rates significantly. Scientists really do not like confusion. The existence of TON 618 challenges models that have been refined over decades. It forces theorists to revisit assumptions about seed masses, accretion efficiencies, and merger rates. It demands explanations that push the boundaries of known physics or invoke rare, extreme conditions. And it is not alone. Several other ultramassive black holes have been discovered at high redshifts, each one raising the same uncomfortable question. How did they grow so large so quickly? The evidence suggests that something rule-breaking occurred in the early universe. Perhaps black hole formation pathways were more diverse than we currently understand. Perhaps the gas dynamics in young galaxies allowed for more efficient feeding. Perhaps mergers were more frequent or more effective at funneling gas towards central black holes. Or perhaps our models of the Eddington limit and accretion physics need revision when applied to the extreme environments of the early cosmos. TON 618 functions as a cosmic cheat code, an object that seems to bypass the normal constraints on growth. Its existence proves that nature found a way to build ultramassive black holes within the first few billion years of cosmic history. Understanding that pathway is one of the major unsolved problems in astrophysics. The discovery of TON 618 and similar objects has opened new lines of research, prompting observations of the early universe with ever more sensitive instruments, theoretical modeling of exotic formation scenarios, and simulations of galaxy evolution under extreme conditions. The mystery deepens when we consider that TON 618 is actively feeding. The quasar phase we observe indicates that gas is still falling in at high rates, sustaining the luminosity of 140 trillion suns. That suggests the black hole has access to a substantial reservoir of fuel even at this late stage in its growth. Where that gas comes from, how it reaches the black hole, and how long the feeding can continue are all open questions. But the fact remains that TON 618 grew impossibly fast, and it is still growing. The mechanisms that enabled that rapid ascent remain one of the great puzzles of modern cosmology. The rapid growth of TON 618 is puzzling enough on its own, but the problem deepens when we examine the physics of how black holes feed. There is a fundamental limit to how quickly a black hole can accrete matter, a boundary imposed not by the availability of fuel but by the radiation generated during the feeding process itself. This limit is known as the Eddington limit, named after the British astrophysicist Arthur Eddington, who first described the balance between gravity and radiation pressure in stars. For black holes, the same principle applies. As matter falls inward and heats up, it radiates energy. That outward radiation pushes back on the infalling gas. If the luminosity becomes too high, the radiation pressure can halt or even reverse the inflow, effectively choking off the black hole's food supply. The Eddington limit is not arbitrary. It is derived from basic physics. For a given black hole mass, there is a maximum luminosity at which the outward force from radiation pressure equals the inward pull of gravity. Beyond that luminosity, the radiation wins and accretion slows or stops. The limit scales linearly with mass. A more massive black hole has a higher Eddington luminosity because its stronger gravity can overcome greater radiation pressure, but the limit still exists, and it sets the maximum rate at which a black hole can grow through accretion under standard assumptions. For a black hole accreting at the Eddington limit, the maximum sustainable luminosity is proportional to its mass. The corresponding accretion rate determines how quickly the black hole can grow. Under continuous Eddington limited accretion, a black hole can double its mass roughly every 50 million years. That exponential growth sounds fast, but over the 3 billion years available in the early universe before we observed TON 618, it translates to a maximum mass of around 50 billion solar masses if you start from a reasonably large seed. 50 billion is large, but it is not 66 billion. TON 618 exceeds even that generous estimate. This is where the problem becomes acute. T 618 has a mass of approximately 66 billion solar masses. That is over the expected limit for what continuous Eddington accretion should produce in the available time. The excess is not trivial. It represents tens of billions of solar masses that, according to standard models, should not be there. Either the black hole grew faster than the Eddington limit allows, or it started from a much larger seed than typical models assume, or some combination of both. Each of these possibilities challenges established theory. One way around the Eddington limit is super-Eddington accretion. Under certain conditions, black holes can accrete matter faster than the standard limit predicts. If the infalling gas is clumpy rather than smooth, or if it falls in along specific directions rather than spherically, the radiation can escape preferentially through low-density channels while matter continues to flow in through denser filaments. This allows the black hole to feed at rates exceeding the Eddington limit without the radiation pressure halting the inflow. Simulations of gas dynamics around black holes have shown that such configurations are possible, especially in the turbulent, gas-rich environments of the early universe. However, super-Eddington accretion alone may not be enough. Even if TON 618 accreted at twice the Eddington rate for the entire 3 billion years available, it would still require a very large seed mass to reach 66 billion solar masses. The math remains tight. Every additional billion solar masses requires an explanation. The black hole cannot simply ignore the laws of physics. It must work within them, even if it pushes the boundaries. Another possibility is that the Eddington limit itself may not apply uniformly in all situations. The classical Eddington derivation assumes a spherically symmetric, steady-state accretion flow. Real accretion disks are far more complex. They are turbulent, magnetized, and threaded with outflows. The radiation field is anisotropic, meaning it does not radiate equally in all directions. If the geometry of the accretion flow deviates significantly from the idealized case, the effective limit could be higher than the classical Eddington value. This would allow the black hole to sustain higher luminosities and higher accretion rates without self-regulating as strongly. There is also evidence that some black holes defy accretion pressure barriers through sheer environmental advantage. In the dense, gas-rich cores of young galaxies, where mergers are frequent and gas is funneled efficiently toward the center, black holes may have access to fuel at rates far exceeding what quieter, mature galaxies can provide. If TON 618 formed in such an environment, it could have sustained high accretion rates for extended periods, growing faster than isolated black holes in less dense regions. Mergers provide another mechanism to bypass the Eddington limit. When two black holes merge, their masses combine instantaneously. No accretion is involved. No radiation pressure limits the process. If TON 618 underwent a series of major mergers in its early history, it could have gained significant mass without ever approaching the Eddington limit for sustained periods. Each merger would represent a sudden jump in mass, followed by a phase of Eddington-limited growth until the next merger. String together enough mergers, and the cumulative mass gain could explain the 66 billion solar mass final product. The problem with the merger scenario is timing. Black hole mergers require galaxies to collide, black holes to sink to the center through dynamical friction, and orbits to decay through gravitational wave emission. Each step takes time. While the early universe was more merger-rich than today, it is unclear whether enough major mergers could occur within 3 billion years to produce such an extreme mass. The statistics of merger rates and the efficiency of black hole coalescence both factor into the calculation, and both are uncertain. TN 618 may also represent a new category of hyper-hungry black holes, objects that formed under such unusual conditions that they do not fit neatly into existing classifications. Perhaps they are the rare endpoints of the most extreme formation pathways, the products of environments so dense and gas-rich that normal growth constraints do not apply. If so, then studying TON 618 and similar objects could reveal new physics about how matter behaves under extreme gravitational and radiative stress. The fact that TON 618 exceeds the expected mass limit has opened doors to new cosmic theories. Researchers have proposed exotic seed formation mechanisms, revised accretion models, and alternative growth pathways. Some theories invoke primordial black holes formed in the first moments after the Big Bang. Others propose runaway collisions in dense star clusters, producing black hole seeds of thousands or millions of solar masses. Still others suggest that dark matter could play a role, either by seeding black hole formation or by altering the dynamics of gas infall in ways not yet understood. What is clear is that TON 618 does not fit comfortably within the standard picture of black hole growth. It is an outlier, an extreme case that challenges assumptions and forces revisions. Scientists have been scratching their heads for decades over how such objects came to exist so early and so massively. The discovery of additional ultramassive black holes at high redshifts has only deepened the mystery. Each new example adds weight to the conclusion that something fundamental about black hole growth in the early universe remains poorly understood. TN 618 is not an anomaly in the sense of being impossible. It is an anomaly in the sense of revealing gaps in our knowledge, places where the models break down and new physics must be invoked. The black hole exists. The question is, how? The mystery of how Ton 618 grew so massive so quickly has forced astrophysicists to look beyond conventional black hole formation scenarios. Standard models assume that black holes begin as the remnants of massive stars, with initial masses ranging from a few to perhaps 100 times the mass of the Sun. Those seeds then grow through accretion and mergers over billions of years. But as we have seen, that pathway struggles to produce a 66 billion solar mass black hole within only 3 billion years of cosmic history. The numbers do not close easily, and so theorists have turned to more exotic possibilities, scenarios that invoke rare conditions, unusual physics, or entirely different formation mechanisms. One of the leading alternative theories is the primordial black hole hypothesis. In this scenario, black holes form not from stellar collapse but directly from density fluctuations in the very early universe, moments after the Big Bang. During the first fraction of a second, quantum fluctuations in the primordial plasma could have created regions of slightly higher density. If these overdense patches were large and dense enough, they could have collapsed under their own gravity before the expansion of the universe could disperse them, forming black holes with masses ranging from tiny fractions of a gram to thousands or even millions of solar masses. If Ton 618 began as a primordial black hole with an initial mass of thousands or millions of solar masses, the growth problem becomes far more manageable. Starting from such a large seed, even standard Eddington limited accretion over 3 billion years could plausibly produce a 66 billion solar mass black hole. The challenge with this theory is that primordial black holes remain hypothetical. We have no direct evidence that they exist, though they have not been ruled out. If they do exist, they could solve not only the growth problem for ultramassive black holes, but also contribute to the dark matter content of the universe. Another exotic possibility involves dark matter itself. Dark matter is the invisible substance that makes up roughly 85% of the matter in the universe. It does not emit, absorb, or reflect light, but it exerts gravitational influence. In regions where dark matter is exceptionally dense, such as the centers of dark matter halos, in the early universe, it could have played a role in black hole formation. One proposed mechanism is dark matter collapse. If dark matter particles can lose energy through some process, they could clump together and collapse into dense cores. These cores could then attract ordinary matter, gas, and dust, triggering the formation of a massive black hole seed. Dark matter could also affect the growth rate of black holes indirectly. If a black hole is embedded in a dense dark matter halo, the dark matter particles could be captured by the black hole's gravity and fall in, contributing to its mass. While individual dark matter particles are thought to be very light, the sheer density of dark matter near the black hole could make this a non-negligible contribution over cosmological timescales. This remains speculative, but it represents one way in which dark matter might influence black hole evolution in ways not accounted for in standard models. A third scenario involves the direct collapse of dense gas clouds without forming a star first. In the very early universe, before the first generation of stars enriched the interstellar medium with heavy elements, gas clouds were composed almost entirely of hydrogen and helium. These clouds could remain very hot because there were no metals to facilitate radiative cooling. Under certain conditions, particularly in the presence of intense ultraviolet radiation from nearby protogalaxies, a massive gas cloud could remain too hot to fragment into stars. Instead, it would collapse as a whole, forming a supermassive star, or, in the most extreme cases, collapsing directly into a black hole, with an initial mass of tens of thousands to hundreds of thousands of solar masses. This direct collapse scenario bypasses the slow, stellar evolution pathway entirely. It produces a massive seed in one catastrophic event, giving the black hole a huge head start. From there, even moderate accretion rates could grow the seed into a 66 billion solar mass giant within the available time. The conditions required for direct collapse are rare, but the early universe was a strange and violent place. In the dense, turbulent environments of the first galactic structures, such conditions may have been more common than they are in the present-day universe. Another possibility is the formation of supermassive stars. In regions of extremely high gas density and low metallicity, stars could form with masses far exceeding anything we see in the local universe. These supermassive stars, with masses of tens of thousands or even hundreds of thousands of solar masses, would be highly unstable. They would burn their fuel rapidly, lasting only a few million years before collapsing. When they collapsed, they would leave behind black holes with masses comparable to the original star. Such a black hole would already be massive enough to grow into an ultramassive black hole like TON 618 through subsequent accretion and mergers. Multiple black hole merger chains also offer a pathway to rapid mass growth. If a young galaxy experiences a series of mergers with other galaxies, each bringing its own central black hole, the black holes can eventually coalesce. Each merger combines the masses of the two black holes, producing a larger black hole almost instantaneously. If TON 618 is the product of a long chain of such mergers, it could have accumulated its mass far more quickly than accretion alone would allow. The key is that mergers add mass without invoking the Eddington limit. They are limited only by the frequency of galaxy collisions and the time required for black holes to sink to the galactic center. There is also the possibility that TON 618 formed in a rare cosmic nuclear zone, a region where multiple extreme conditions coincided. Perhaps it formed at the intersection of several massive dark matter filaments, where gas was funneled in from multiple directions. Perhaps it was located in a particularly dense cluster of protogalaxies, where mergers were exceptionally frequent. Perhaps the gas chemistry, temperature and ionization state were just right to allow super-efficient accretion. Any combination of these factors could have created a unique environment that allowed rapid black hole growth under circumstances that are difficult to replicate elsewhere in the universe. The challenge with all of these exotic theories is that they are difficult to test directly. We cannot observe the formation of TON 618. We can only infer its history from its current properties and from comparisons with other black holes. Each theory makes predictions about the statistical distribution of black hole masses, the environments in which ultramassive black holes should form, and the signatures left in the surrounding gas and stars. By comparing these predictions with observations, astronomers can constrain which formation pathways are plausible. What is clear is that TON 618 could be a bridge to unknown physics. Its existence challenges every formation model and forces us to consider possibilities that seemed unlikely or exotic only a few decades ago. It may be part of a family of megagiants, rare objects that represent the extreme tail of the black hole mass distribution, or it may be unique, the product of conditions so unusual that they occurred only once in the observable universe. Either way, TON 618 remains an unsolved cosmic riddle, a monument to the fact that nature is capable of producing outcomes far beyond what our simplest models predict. The black hole exists, The question of how it came to be remains open, inviting new observations, new theories, and new physics. The existence of TON 618 is not just a curiosity for black hole physics. It is also a window into one of the most fundamental processes in the universe, the evolution of galaxies. Over the past few decades, astronomers have come to realize that supermassive black holes are not passive passengers at the centers of galaxies. They are active drivers influencing the shape, growth, and star formation history of the galaxies that host them. The relationship between black holes and galaxies is so tight that the mass of the central black hole correlates remarkably well with the properties of the surrounding stellar bulge. TON 618, with its extreme mass, represents the upper end of that relationship and offers critical insights into how the largest structures in the universe came to be. Observations over the last 30 years have revealed a striking pattern. The mass of a supermassive black hole at the center of a galaxy is typically about 0.1 to 0.5% of the mass of the stellar bulge, the dense central region of stars. This is not a loose correlation. It holds across a wide range of galaxy types and masses, from small elliptical galaxies with black holes of a few million solar masses to giant ellipticals harboring black holes of billions of solar masses. The tightness of this relationship suggests that black holes and galaxies grow together, influencing each other through feedback mechanisms that regulate both star formation and black hole accretion. The mass of a black hole directly affects the shape and growth of its host galaxy through a process known as feedback. As the black hole feeds on surrounding gas, the accretion disk emits enormous amounts of radiation and often launches powerful jets of charged particles at near light speed. This energy output heats the gas in the galaxy, ionizing it and driving winds that can expel material from the galactic core. The result is a reduction in the amount of cold gas available for star formation. In effect, the black hole regulates its own growth and the growth of the galaxy by heating and expelling the very fuel it needs to continue feeding. For a black hole as massive as TON 618, the feedback effects must have been dramatic. A 66 billion solar mass black hole radiating at the luminosity of 140 trillion suns does not just heat nearby gas. It transforms the entire galactic environment. The radiation pressure can drive winds at velocities of thousands of kilometers per second, clearing out gas from the central kiloparsecs of the galaxy. The jets, if present, can punch through the interstellar medium and inject energy into the halo, heating gas to millions of degrees and preventing it from cooling and collapsing to form new stars. This feedback process has profound implications for galaxy evolution. Without it, galaxies would continue to form stars at high rates for much longer, potentially exhausting their gas supply and producing stellar populations very different from what we observe. The presence of an active supermassive black hole acts as a thermostat, keeping the galaxy in balance. When too much gas accumulates in the center, the black hole feeds more vigorously, heats the gas, and shuts down star formation. When the gas supply dwindles, the black hole quiets and star formation can resume. Over billions of years, this feedback cycle shapes the final structure of the galaxy. TON 618 teaches us about the extremes of this relationship. Its mass places it far above the typical scaling relation, suggesting that its host galaxy must have been unusually massive, or that the black hole grew in an environment where feedback was less effective at halting accretion. Either way, studying TON 618 helps refine our models of galaxy evolution. it shows that the relationship between black holes and galaxies can be pushed to extraordinary limits, and it provides a test case for theories that predict how feedback operates in the most extreme systems. The influence of supermassive black holes extends beyond their immediate surroundings. The energy injected by quasars like TON 618 can affect the large-scale structure of the universe. In the early universe, when quasars were more common, their combined radiation output helped to ionize the intergalactic medium, clearing the fog of neutral hydrogen that filled space after the Big Bang. This reionization process was critical for the formation of later generations of galaxies. Without it, the universe would have remained opaque to ultraviolet and visible light, and the formation of structure would have proceeded differently. TON 618 also helps us understand the distribution of star formation in galaxies. Observations show that the most massive galaxies tend to have lower rates of star formation than expected, given their gas content. This is known as quenching, the process by which star formation is suppressed. Feedback from supermassive black holes is one of the leading explanations for quenching. By heating and expelling gas, black holes prevent the galaxy from converting its remaining gas into stars. TON 618, as one of the most massive black holes known, is an extreme example of a system where feedback must have been extraordinarily powerful. The connection between light and darkness, between the luminous accretion disk and the invisible black hole, is central to understanding galaxy evolution. The light we see from TON 618 is evidence of the black hole feeding. That feeding process releases energy that shapes the galaxy. The radiation heats gas, the jets drive winds. The gravity of the black hole organizes the orbits of stars and gas in the central region. All of these effects ripple outward, influencing the galaxy as a whole. In this sense, black holes are architects of cosmic structure, building the galaxies we observe through a combination of gravitational attraction and energetic feedback. TON 618 also provides a glimpse into the life cycle of galaxies in the early universe. The quasar phase we observe is a transient state. The black hole is actively feeding, shining brightly, and likely suppressing star formation in its host galaxy. Eventually, the gas supply will be exhausted or expelled, and the quasar will shut down. The black hole will remain massive and dark, at the center of a quenched galaxy filled with old stars. Billions of years later, that galaxy may merge with others, triggering new episodes of star formation and black hole feeding. The cycle repeats, driven by the interplay between gravity, gas dynamics, and feedback. By studying TON 618 and similar objects, astronomers can trace this cycle across cosmic time. They can measure how black hole masses correlate with galaxy properties at different epochs. They can observe how feedback affects star formation rates. They can test models of galaxy formation and evolution against real data. TON 618 is not just an isolated object. It is part of a larger story, the story of how galaxies and black holes grew together from the chaotic conditions of the early universe into the structured systems we see today. The extreme feedback from TON 618 also serves as a reminder that black holes are not just consumers, they are also regulators. They do not simply drain energy from their surroundings, they inject energy back, shaping the environment in ways that affect the entire galaxy and beyond. This dual role as both gravitational sink and energetic source makes supermassive black holes central players in the cosmic drama of structure formation. TON 618 is the ultimate architect in this sense, a black hole so massive and so luminous that its influence must have dominated its host galaxy and perhaps even extended into the surrounding intergalactic medium. Understanding that influence is key to understanding how the universe evolved. From the smooth, nearly uniform state shortly after the Big Bang into the rich tapestry of galaxies, clusters, and voids we observe today. The story of Teen 618 is, in the end, a story about limits. It is about how far nature can push the boundaries of mass, energy, and scale. It is about the limits of human understanding and the tools we build to overcome them. And it is about the humility required to accept that the universe operates on terms far beyond anything our species evolved to comprehend. TON 618 does not ask for our understanding. It does not care whether we can explain its existence. It simply is. And in being what it is, it forces us to confront the smallness of our perspective and the vastness of the cosmos we inhabit. This is a reminder of cosmic humility. Every human being lives on a planet that orbits an average star in an unremarkable region of a typical spiral galaxy. That galaxy, the Milky Way, contains hundreds of billions of stars and is itself one of hundreds of billions of galaxies in the observable universe. Within that incomprehensible expanse, TON 618 exists as a singular extremity, a black hole so massive that it outweighs our entire galaxy. The scale difference is almost meaningless in practical terms. We cannot visit TON 618. We cannot interact with it. We can only observe its ancient light and attempt to understand what it tells us. Yet in that observation lies something profound. The light from TON 618 has travelled for over 10 billion years to reach us. It crossed intergalactic voids, passed through clouds of hydrogen, redshifted as the universe expanded, and finally arrived at a small blue planet where curious beings pointed instruments skyward and captured the photons. Those beings decoded the information embedded in the light, inferred the existence of a 66 billion solar mass black hole, and built mathematical models to explain how such an object could form. In that act of observation and interpretation, something remarkable happened. The universe became aware of itself. Reality exceeds imagination. Before TON 618 was discovered, no one could have confidently predicted that such a massive black hole existed. Theoretical models suggested upper limits, but those limits were based on assumptions that turned out to be incomplete. The universe does not respect our assumptions. It produces phenomena that challenge and exceed our best efforts to predict and explain. TON 618 is proof that no matter how sophisticated our theories become, nature will always have surprises in store. The cosmos is richer, stranger, and more extreme than any model can fully capture. The universe is still full of secrets. Despite centuries of astronomical observation and decades of modern astrophysics, we have barely scratched the surface of what there is to know. We do not fully understand dark matter or dark energy, which together make up 95% of the universe's content. We do not know what happens inside a black hole's event horizon. We do not know whether there are other universes beyond our observable horizon. Every answer we find generates new questions. Every discovery reveals deeper layers of complexity. TON 618 is one piece of a much larger puzzle, a puzzle so vast that it may never be fully solved. Black holes shape existence. They are not passive objects sitting quietly at the centres of galaxies. They actively influence star formation, gas dynamics, and the large-scale structure of the universe. They regulate galaxy growth through feedback. They ionize the intergalactic medium through their radiation. They merge and generate gravitational waves that ripple through space-time. In the early universe, black holes like TON 618 played a crucial role in transforming the cosmos from a smooth, nearly uniform state into the rich tapestry of structure we see today. They are architects, engines, and regulators all at once. Space is too huge to comprehend. The event horizon of TON 618 stretches over 1,000 astronomical units. A single astronomical unit is the distance from the Earth to the Sun, a distance so large that light takes 8 minutes to cross it. Scale that up by a factor of 1,000, and the numbers cease to have intuitive meaning. We can write them down, we can calculate with them, but we cannot truly picture them. The human brain did not evolve to visualize distances measured in billions of kilometers or timescales measured in billions of years. We are pattern recognition machines adapted for life on a small planet, and the universe is not small. TON 618 shows how little we know. For all the progress made since 1957, when it was first catalogued as a faint blue star, fundamental questions remain unanswered. We do not know exactly how it grew so massive so quickly. We do not know what its host galaxy looks like in detail. We do not know whether it is still feeding or whether it has quieted since the epoch we observe. We do not even know for certain whether it is the most massive black hole in the universe or simply the most massive one we have found so far. Each piece of missing information is a reminder that our knowledge, while impressive, is still limited. Our curiosity drives discovery. The entire history of astronomy is a history of looking up and asking questions. What are those points of light in the sky? Why do they move? What are they made of? How far away are they? Each question leads to new tools, new techniques, and new answers. The invention of the telescope, the development of spectroscopy, the launch of space-based observatories, the construction of gravitational wave detectors. Every step forward is motivated by the desire to know, to understand, to see further and more clearly. TON 618 is a product of that curiosity, a discovery made possible by generations of astronomers pushing the boundaries of what is observable. We keep asking bigger questions. Why does the universe exist? How did it begin? How will it end? Are we alone? What is the nature of space and time? These are not small practical questions. They are fundamental inquiries into the nature of reality itself. TON 618 does not answer those questions directly, but it contributes to the framework within which we seek answers. It shows us that the universe is capable of producing extremes far beyond everyday experience. It challenges our models and forces us to refine our theories. In doing so, it brings us closer to a deeper understanding of how the cosmos works. The cosmos is still evolving. The universe today is not the same as the universe 10 billion years ago, when the light from TON 618 began its journey. It has expanded. Galaxies have merged. Stars have been born and died. Black holes have grown and quieted. The large-scale structure has become more pronounced as gravity pulls matter into filaments and clusters. And this evolution continues. Billions of years from now, the universe will look different again. Galaxies will be farther apart. Stars will be dimmer and redder as the brightest, most massive stars exhaust their fuel. Eventually, on timescales almost too long to conceive, even black holes will evaporate through Hawking radiation. The cosmos is not static. It is a dynamic, evolving system, and TON 618 is a snapshot from one moment in that evolution. TON 618 is the ultimate universal flex. It is nature showing off, demonstrating that the universe is capable of producing objects so extreme, so massive, so luminous, that they defy easy comprehension. It is a gravitational titan, a quasar blazing with the light of 140 trillion suns, a black hole with an event horizon that could swallow our entire solar system and still have room to spare. It is a challenge to our models, a benchmark for future discoveries, and a reminder that the cosmos operates on scales that dwarf anything in human experience. It is proof that reality is stranger, more extreme, and more awe-inspiring than anything we could have invented. And in the end, TON 618 is a message from the abyss. It tells us that the universe is vast, ancient, and filled with wonders beyond imagination. It tells us that we are small, brief, and limited in our understanding. But it also tells us that we are capable of reaching across billions of light years, capturing ancient photons and decoding the stories they carry. It tells us that curiosity, patience, and collaboration can unlock secrets that once seemed forever beyond our grasp. TON 618 is not just a black hole. It is a testament to the human drive to explore, to question, and to understand the universe we find ourselves in, no matter how strange or distant its mysteries may be.